Okay, I think this is about where we finished, but is this, yeah, that looks like what the last thing we wrote down. Can I just redo this question? I know you have it in front of you. Can I redo it just to kind of remind you what we were doing last day? Can you guys grab that door while I get started here? The basic concept behind this question, I think I told you the story. I had a new couch that was supposed to show up at my house, and there was supposed to be a wall, and I wanted to figure out how much angle of recline does there need to be. That's not 105, that's 150. In my couch, so that like when I put the couch a certain distance away from the wall, the couch like just barely touches the wall. It doesn't like hit the wall. Does that concept make sense? So essentially I drew a triangle inside here that hopefully you guys drew. And that triangle, even though this angle around to here was 150 degrees, this triangle was 30 degrees. Okay. Right off the bat, I need to remind you of the special triangles is what we talked about last day. If you ever are given an angle of 30 degrees, 45 degrees, or 60 degrees, we can use one of the special triangles to do like a substitution trick to help us get an exact value rather than a rounded value. Do you guys remember those triangles? If you don't have them written down somewhere, make sure you write them down. One is a 1, 2 with root 3, and there's a 30 and a 60. And the other one is a 1, 1 with a root 2, and either way the angle's 45. If you don't have that written down somewhere, you really should. Okay, so back to my question here. Basically what it tells you is that the chair is 104 centimeters, and we're looking for x right here, the distance the chair has to be away from the wall. So to solve that, we used SOHCAHTOA, sine, cosine, or tan. If 30 right here is my angle, this side right here would be opposite, this side here would be adjacent, and this side here would be hypotenuse. So we need to use the trigonometric, the word we use, by the way, is trigonometric identity. That's like the terminology we use, but I don't care what you call it for now, I guess. But we need the one that involves adjacent and hypotenuse. So that's cosine. So you'd say something like cosine of your angle is your adjacent over your hypotenuse. You know the angle, the adjacent, I guess I should write the angle in then if I know the angle. Cosine of theta is 30. The adjacent is x and the hypotenuse is 104. How do you get x by itself? Take the 104, times it up to the other side. So you get 104 cosine 30. This, I think, is where most of you guys were okay with last week. And then the next step is the one that kind of started screwing people up. Rather than typing 104 cosine 30 in your calculator and getting a decimal number, sometimes it's preferable to try to find what's called an exact value. Now, I need to point out, like 99% of cases, exact values aren't necessary. Like rounding is probably acceptable. But I hope you guys would agree that there are some certain times where you don't want to round. Like rounding will cause an error. Like if you're NASA sending a spaceship to Mars, even the slightest bit of error will cause that spaceship to miss Mars, and then you've wasted $1 billion, and Matt Damon can't come back home again. Saw the movie? So, but like 9 times out of 10, 99 times out of 100, exact values aren't necessary, but I do want you guys to know how to work with them. So the concept here is we're going to do a substitution. Rather than writing cosine of 30, we're going to use this triangle here to figure out what cosine of 30 can also be written as. In this triangle right here, the cosine of 30 would be the adjacent to the 30, which would be the root 3, over the hypotenuse, which would be 2. This is your adjacent and your hypotenuse compared to the 30. So rather than writing cosine 30 right here, we just write 104 and then write root 3 over 2. Which means that 104 and 2 can actually divide by each other, and it gives you 52 root 3s. And this is now considered to be exact. There's no rounding required whatsoever. Does that make sense? So that's kind of where we left off last day. So I just want to finish off whatever we didn't finish. Then we'll take a break and then we'll do the next set of notes. Here are some angle definitions I'd like you guys to know. Basically the terms are supplementary and complementary. If this angle right here is 150 degrees, this angle right here has to be 30. And the reason why is that these two angles are on a line, and angles on a straight line have to equal 180. That's called supplementary. If this angle right here, for example, was 42 degrees, what would this angle right here have to be then? Anybody know? Yeah, because these two angles have to add to give 90. You guys ever seen those properties before, or is that new information? You've seen that before? Okay. Oh, okay, maybe not. Either way, like if I give you a question, I might not give you the angle you think you're looking for. I might give you a different angle, and then you have to kind of solve for the angle you're actually solving for. Like in this question we just did here, the chair itself was 150. Did we ever actually type 150 into our calculators or something like that? No, we didn't use the 150 because it was the 30 degrees right here that was actually part of the triangle we were using. Does that make sense? Okay, more terminology after that then. You know how we can graph things? We can graph things in trig too. It's like taking the two worst things in the world and like making a sandwich with like the two grossest things you can imagine. Graphing and trigonometry shoved together. It's like peanut butter and sardines or something. Okay, that's actually not that bad to start with. I really try to do a thorough job of talking about this in grade 11 because this is the core of what we do in trigonometry in grade 12. So I'm going to go into maybe just a little more detail than you might need, but you need it next year anyways. So basic concept here is imagine you have an XY coordinate plane. What we're going to do is we're going to define the initial side of an angle as always being on the x-axis. That's been chosen as like a standard definition. So one side always goes on this axis here. Well, then you can always have like an angle where the other part of the, angle, we call it the terminal side. It can be in any of the different four quadrants. Okay. This angle right here would be, say, 150 degrees, for example. Does that make sense? But I can plot it on an actual grid. The reason why this is useful is that we can actually use coordinate points. Like this point right here, for example, could be -6, 7. Because you've gone backwards 6 and up 7. That makes sense. Anybody ever played Battleship before? Yeah. When I think of this at first, I think of Battleship, where you've got like your grid, and then you say C4, A2, right? And you kind of have a grid going on here. Granted, you don't have a grid because it's not letters and numbers, it's numbers and numbers. But we can actually use that, try to figure out angles and how they work in relation to each other. Do you guys know what an origin is? Do you guys know that word? Okay. Do you know what it is in math context? You guys don't, apparently. Okay, this right here is the origin. 0, 0 is defined as the origin, if you've never heard that before. Okay. The point of the triangle that we're going to make is always going to be at the origin. Let me show you some examples of how I mean to use this. See how in this angle right here, it's 45 degrees. The initial arm is on the x-axis, and then here's an angle there at 45. Okay. What you could do though is you could actually even have an angle like say all the way around. Here is a very, very large angle of 315 degrees. It's like you're going all the way around in a circle, and really what you're actually lacking is like this little bit is actually the part that you're missing. But the angle itself is like all the way around the circle. Or say in this quadrant here, this is 225 degrees because you're going all the way past 180 and you're going a little bit further, in fact. So it means we can actually work with angles of anywhere between 0 and 360. Has anyone ever talked to you about the different quadrants that you have on a graph? You guys know quadrant 1, 2, 3, 4? Yeah. Okay. The picture I want to show with this then is, let's say that you have this angle down here in the third quadrant, where it's like going all the way around the circle a little bit. What you can actually do is you can make a triangle, a small little triangle, in this quadrant right here. You guys see how I'm throwing a little purple triangle in there? This little angle right here has a word. It's called a reference angle. And we can usually calculate reference angles with just a simple calculation. I'm going to do an example in a second. Just give you a second to write that down. But it's often typical that you can write a triangle in like a different quadrant. You can make triangles there. Let me do an example. Let's say that from here to here is 200 degrees. So we're starting over here on the x-axis, as is typical. And I'm giving you an angle slightly more than 180 degrees. Does that make sense so far? 200 degrees. Well, the reference angle triangle then would be a triangle that looks like this. I'm going to go draw back up to the axis and draw a little triangle in like this. What would that little angle inside there be? Anybody know?
20.
It would be 20, yeah. Why?
Because a flat line.
Yeah, like a flat line all the way across is 180. So if you go a little bit past 180 to get to 200, how much bigger is 200 than 180? 20. Does that logic make sense? So what we actually have is, although the angle all the way around is 200, what we actually can work with then is a little triangle that goes 20 degrees in the corner instead. And it has a nice little right angle, so we can actually do all of our trigonometry stuff we've been doing, all, like Pythagoras' theorem, SOHCAHTOA, all that stuff. Just as a quick example then, let's just sketch some of these angles to make sure you know what they'd look like. Where would 150 degrees be? Okay, well, start here. So here's a line to start with. Straight up right here, that would be 90. Does that make sense? All the way across over here would be 180. So 150's got to be like, I don't know, ish, like that. That's 150 degrees. Okay, don't draw what I'm going to draw next. Just watch this next part. I just want to show a point. There is a triangle right there. Can you guys see how there's a line here, a line here, a line there is an obtuse triangle? There's a problem with working with that triangle, though. It's not 90 degrees. Does that make sense? That's a major issue. So rather than working with that triangle, now draw this. It's actually preferable maybe to draw a triangle like this. So I've drawn a triangle there instead. What would the angle inside there be then? Good, yeah, 30. Because 30 and 150 adds to 180.
Oh, so you just take like the 150 and
Just subtract it, basically subtract from 180. That makes sense. So this right here is known as a reference angle. Let me try another one. Where would 60 degrees lie? Well, if you have to draw something right along the axis to start with, straight up would be 90, right? So 60 degrees would just be right in this quadrant right here. Actually, I don't really need to draw any sort of weird triangle, because to be honest, the triangle is already just sitting there anyways. It's 60 degrees is what I'm working with. So in this example here, the reference angle is 60 degrees. There's nothing really weird there. Where would 240 end up at? So again, I'll draw a thick line along the axis here. This would be 90, right? That'd be 180. Well, actually, let's talk about this. Where would the line down be? What would that be?
270.
Good, yeah, 270. Yeah, and then like all the way around the circle would be 360. So 240 is actually in this quadrant-ish somewhere. Okay, now 240 is like the outside of this angle. So this angle goes all the way around like that, giving you 240. Don't draw what I'm about to draw here. In theory, you could draw a triangle like this. There's a triangle there. The only problem with that, it's not a right angle triangle. So that kind of limits our options. So we don't do that. What we do instead is we draw a triangle. And by definition, we always draw the triangle to the x-axis. So from this point right here, I'm going to draw straight up to the x-axis. And we're going to make a triangle right there instead. What would this little angle right here be then?
60.
60 is correct, yeah. How'd you guys get to 60 though?
Subtracted 180 from 240.
Exactly, yeah. If 240 is all the way around to here, but 180 is like the flat halfway, well, not halfway mark, but I guess halfway makes sense, right? If 180 is to here, but you go a little bit further than 180, well, if you take 180 and subtract 240, this little angle here is 60. So what you could do is work with this triangle here instead. You could work with a right angle triangle with a 60 degrees and a quarter. So let's do some more examples now. I think that now that I've shown you some stuff, let's try another example of a word problem. So again, I don't know what inspired me for this question here, but I was imagining someone who's doing like leg lifts in the gym. And I realized there's an angle in there. I promise you, there's geometry everywhere in the world. There's an angle right here. Can you guys kind of imagine that here are his legs, and then right down there are his shins. And hopefully you can envision that there is an angle all the way around there. And I'm going to tell you that that angle is 240 degrees. You guys can picture that? I'll even draw it out maybe in another location here. So almost like imagine like a grid. Here are his thighs. Here are his shins. And all the way around is 240. Okay, I need to read a couple more things here. It says the height of the chair is 34 inches above the ground. What does that mean? Well, it means that this height right here is 34 inches. So it's almost like, if I kind of extend my picture here, from here down to here is 34 inches. Is that 34 inches something I can plot on my, something I can actually plot on my triangle? No. It says that when his knees are bent at a right angle, though, his feet are exactly 5 inches off the floor. So, like, imagine that his legs could, like, swing back down to right here. If he was, like, perfectly flat, you know what I mean? Like, kind of like how my knees are at like this. It says that there would be 5 inches left. Can you just kind of picture that? How long are his legs? Yeah, 29. That makes sense? Because from here to the floor is 34, but then there's 5 inches left over. So what I'm basically telling you is that from here to here is 29. Maybe I'll even use another color for that. Pen red. From here to here then must be 29 inches. Okay, well again, that doesn't actually help me with a triangle yet. But can you kind of see how if from my knee to the bottom of my foot, if that's 29 inches, then as I swing that out, is it not still 29 inches as it's swung outwards? Basically what I can tell you now is that it's 29 inches on that hypotenuse right there. His legs are 29 inches, or at least from his knee to his feet. I can draw a triangle then. Here's a triangle that looks like this. That's 29 inches. It's almost like I'm drawing a triangle right there. Does that make sense so far? Okay. I know an angle. Or at least, hopefully you can find that angle right there. If all the way around is 240, what's the little reference angle? 60. We did that one a few minutes ago, right? Where 60 is the extra little bit there. So you got like a 60 degrees right here. Okay. What are we being asked to solve for? Okay. So like for this diagram right here, what we're really being asked for is this distance right here. We don't know how high his feet are above the ground. Does that make sense? Like this from here to here. That x value is what I'm being asked to solve for. Any ideas how to find that number?
Like it's going to be the same as.
What we ultimately need to do is find this side right here. Why don't I call that side y right there? If I find y right there, what's the relationship between y and x? That's the kicker, yeah. 34 is how high the chair is off the ground. 34, I'll even write this in black right here. 34 inches is how far it is from here to there. All of that's 34 inches. So the height that is above the ground, x right here, is actually whatever y is. X plus y is going to be 34. So if I want to figure out how high he is above the ground, I just need to subtract it from 34. Well, this y right here is the y right there. And that inset triangle I just drew. The great news, though, is I found a way to, although there's a lot of interpretation here, I found a way to make it so I have a right angle triangle. There's a 90 degrees sitting right here, 60, 29, and unknown y. Okay, compared to the 60, what is y? Opposite adjacent hypotenuse. 29 would be, which trig identity involves opposites and hypotenuses. Hypotenuses. I don't know what the plural is. Sine, yeah. So the sine of 60 is the opposite, that's y, over the hypotenuse, which is 29. How do you get y by itself? Yeah, multiply up to 29. So y is going to be equal to 29 times the sine of 60. Okay, if you type that in your calculator, though, you get a decimal number. And like I said, most of the time it's not really an issue. But I do want you guys to know how to do this exact value thing. So what else is sine 60 equivalent to? Hopefully you kind of have a triangle drawn somewhere that you can use. Yeah, like a lot of times it's root 3 over 2. So rather than writing it as 29 sine 60, then say that y is equal to 29 root 3 over 2. Okay, well, last step. 29 root 3 over 2s, if you like my drawing right here, is... Oh, that's not going to show up very well. Let's try a highlighter. No, that's still not going to show up very well. Yellow? There we go. Okay. This right here is 29 root 3 over 2, from here to here. And what we're actually asked for is this little distance right here. So x is going to be equal to 34 minus 29 root 3 over 2. This is as exact as we can be. And to be honest, I actually prefer if you leave it like that. Don't give me decimal numbers if I ask for an exact value. Does that not show up very well for you? I'll write it again. So x is equal to 34, that's how far it normally is, minus 29 root 3 over 2.
Is that 29 on the top of the fraction?
Yeah, like the 29 times is by the root 3, then divide by 2.
So
You could write it like this, 29 over 2 root 3. You could write it as 29 root 3, then divide by 2. Both of those would be kind of the same kind of thing. Does that work?
Yeah.
Shelby, you had a so that you were starting. Is that cover what you're looking? Does that make sense in terms of where we're going to start kind of going in this section here? The questions are, I'm going to try to find, to the best of my ability, very real-world, purposeful questions. Well, I mean, I don't know if you ever actually care how high your legs are in the air, obviously, but try to find something where their angles do exist, right? Let's try one more, and then I think this is my last slide, right? Okay, then we'll take a break here. So, anybody know what a metronome is, or how they get used? Like it basically like clicks back and forth side to side. Okay. So what I'm going to tell you here is the pendulum arm itself, right here, this is 10 centimeters. And what it's going to tick back and forth from 45 degrees to 135. So if I were to sketch that, 45 degrees would be in this quadrant right here. And then the pendulum swings all the way to the other quadrant, and it goes to 135. 135 is basically like around to this. So the pendulum goes tick tock, back and forth like that, right? My question is, how much horizontal distance does the tip of the metronome swing? What does that mean? That'll work. Basically, I'm asking you, how far is it from here to there? There's actually two main ways you could solve this question. One of them is to recognize, hey, look, I've got a triangle right here. I'm going to draw it in red. See, there's a triangle right here. This hypotenuse is 10. And really what I need to look for here is x. And then there's a second triangle. Let me show you the second triangle. There's a triangle over here in purple. What's the hypotenuse, though? Still 10, still the same arm, and I'm looking for y. If I want to find the total distance across, I just take x and y and I just add them to each other. Does that make sense? What's the angle sitting in this little triangle here, though? It is 45, yeah. Why is it 45? Yeah, 180 subtract 135 is like there's 45 degrees left over. Honestly, it's the exact same triangle, just symmetrical. So here's what I'm going to do. I'm going to solve this triangle for x. And then when I'm done, I'm just going to times it by 2. So how do I take this triangle and solve for x? That's the adjacent. That's the hypotenuse. That's the opposite. So what involves adjacent and hypotenuse? Good. Yeah, cosine. So cosine of theta is adjacent over hypotenuse. But we know cosine of theta is 45. We do not know that adjacent, but we do know the hypotenuse is 10. Yeah, so do 10 times whatever the cosine of 45 is. Okay, then we just got to figure out what's the cosine of 45. Uh, 45 is that 1, 1, √2 triangle. So the adjacent, I don't care which angle you pick, but the adjacent is definitely 1, and the hypotenuse is √2. So rather than writing cosine 45, write 1 over √2 instead. And then that's actually only just x. X is actually just half of the horizontal distance it travels, so just double it. So if you take all of that and times it by 2, it's 20 over √2. There is our exact value. So that should say times by 2. That's like the world's worst 2. Does that make sense? Okay, let me show you another way you could have solved this. Because often in trigonometry, there's more than one approach. There's actually more triangles inside here we could work with. Do you see how there's a triangle right? Oh, I want black. There's a triangle right here to there to there. Do you guys see how there's a triangle sitting right there? If I were to take that triangle and maybe kind of, well, I'll just redraw it over here, like this to this to this. This side right here would be 10, and that side right there would be 10 as well. There's only one problem. Normally I've been skipping those triangles because triangles are only good to us if they're 90 degrees. There's something really cool about this. If there's 45 degrees right here and 45 degrees right here, that's 90. Well, that means the leftover bit in here would actually have to be 90. This is rare, but we actually at this point can actually solve this using Pythagoras' theorem. Because what you have is 10 squared and 10 squared equals c squared. So an alternate method of doing it would be to say 10 squared plus 10 squared equals c squared. So that's 100 plus 100 equals c squared. C squared equals the square root of 200. Or c equals the square root of 200. Okay, if you use your calculator and take 20 and divide by root 2. Let's get the calculator here. 20 divided by root 2. You get 14 basically. And if you take the square root of 200, you will also get the same answer. This is actually why I do our first unit first, though. We should actually have the math skills needed to be able to prove these things are the same as each other using like our first unit skills. How can you break down a root 200? That'll work. 100 times by 2. Why did you pick 102? Yeah, 100 actually square roots, right? What does 100 actually square root to? 10. That makes sense? So you could call this thing 10 root 2. Well, the other one I was working with right here, you've been asked to take 200 and divide by root 2. It's been a while since we've done this, but do you guys recall the term rationalizing the denominator, where you want to get rid of the square root on the bottom? To do that, you times by root 2 over root 2. It's been a while. Here's actually a practical use for why you do that. If you're ever wondering why is this useful, this is a place where you might need this. If you times by root 2 over root 2, it's just like times by 1, right? On the top, then you'd have 20 root 2. And on the bottom, when you do root 2 times root 2, it is literally the number 2. Because root 2 times root 2 is like you're peeling off the square roots, right? Well, what's 20 divided by 2? 10 root 2. Look, they were equivalent. Two different ways to get the same answer. Does that make sense? Okay, go take a break. Sorry, I'm going to be talking to you all class. This is the way it is. When you come back, we'll try the next topic. More or less, I just need to do a bunch of stuff though before we start doing any sort of like assignments and stuff. I apologize. Okay, so third kind of topic then. I really want to focus on sine, cosine, and tan, and how we can use them in solving problems a little bit more. What I do want to do is introduce to you, though, 3 more things that are not part of SOHCAHTOA. I was saying to Forster, actually, if you guys heard, I wanted to show you these words now so that next year when we use them more, you'll know the terminology. I'm not going to make this a big or really any part of some sort of test. I want you to know these terms. Okay? You know how sine is supposed to be opposite over hypotenuse? Well, if you were to flip that fraction upside down and make it hypotenuse over opposite, that actually has a name. It's called a cosecant. Literally, all you do, though, is take the 2 sides that you were dividing and you flip them upside down.
Why would you do that?
Honestly, I actually don't really have a great reason for why. It's just a definition.
Is there a reason
Sorry.
for it?
Grade 12 diploma exams? No, honestly, there really isn't a use for it. Sorry. I want to introduce the words so you guys have seen them before. Cosine. What that means to do is, cosine is normally adjacent over hypotenuse. A secant is hypotenuse over adjacent. You flip them. Do you guys remember what you call it when you take a fraction and flip it upside down? Good, yeah. So the reason why I want to show this is I need to make sure you guys know a difference in notation. Okay. If I tell you to do sine -1 like this, this notation means right here, this is how you find an angle. If I ask you to inverse sine something, that's how you find an angle. But if I write it like this, sine of theta, and then I write a -1, what this means is it's cosecant. The -1 afterwards really means that rather than writing it as opposite over hypotenuse, it means write it as hypotenuse over opposite and flip it upside down. I just want to show you this now. Honestly, it has no impact on our lives, though. But just the concept of where the -1 goes. If you put the -1 right here, it's called an inverse. If you put the -1 right here, it's called a reciprocal.
What is it equal to reciprocal?
Okay, so the reciprocal basically means take the fraction and flip the fraction upside down. And so in this example here, sine reciprocal is something called cosecant. Cosine reciprocals to something called secant, and tan reciprocals to something called cotan. Andy, your question a while ago, like, why would you use them? To be honest, no one ever does. Okay, that's actually why your calculators only have buttons on them for sine, cosine, and tan. Because with sine, cosine, and tan, you can do everything you need to. So these ones here, like I pulled this picture off the internet, you rarely, if ever, actually need to use those ones. I just want to make sure you know the difference between them. Don't put the -1 afterwards. It makes a huge difference. So like if you use your graphing calculator and you want to find an angle, don't do that. That's totally not going to work. What you need is this
Will it just
sign.
give us an error?
It'll probably give you an error, yeah. It'll probably give an error sign.
And you know it messed up.
Does that subtle difference as to where the -1 goes, does that make sense to everybody? If the -1 is in between, you're actually solving for the angle. If the -1 is afterwards, you're reciprocalizing, there's a verb, and it means you're flipping the fraction upside down.
So if it's not going to give us, like, if our calculator will give us an error, then how are we supposed to find the reciprocal?
To find a reciprocal, all you do is you just take the, like for example, if I ask you for, say it's like cosine of 0.2, then you just put like a -1 afterwards.
Yeah.
This would be how you'd find secant. Okay, that was really weird that it was 1. So since you can't actually type in secant in your calculator, you type in cosine, and then you put the -1. That makes sense? That'll find you a secant. If you were to do this is actually finding you an angle, though.
Yeah.
You get the difference there?
What would you be finding then?
Nothing. Again, secants and cosecants really are not that purposeful. So it's not something that I need you guys to be able to work with. I just want you to know what they are.
So you're not going to, like, give us a question?
No.
So we can find it?
No. Like secant, cosecant, and cotan have, like, I do my very best to try to find the purposefulness in math everywhere. I have given up on trying to figure out where those 3 things are useful. Okay? So. Okay, basically it means that there are then 6 ratios. We only work with the first ones, though. So I just need you guys to know how sine, cosine, and tan work. So sine is opposite hypotenuse, adjacent hypotenuse, opposite adjacent. But I just need you guys to know that it is in theory possible to go hypotenuse over adjacent, hypotenuse over opposite, adjacent over opposite. Those are, in theory, things you could use. You won't. More pictures, but honestly, this is getting silly. So let's just go to this example here. Hypothetically, let's say I give you this triangle right here. This side's 11, this side's 4. Could you guys figure out what this remaining side right here would be? How? Yeah, Pythagoras' theorem will work. A squared plus b squared has to equal c squared. Keep in mind the 11 is the hypotenuse, right? So how do I solve for a? That'll work. So is that 121 minus 16? I got 105. So it's actually the square root of 105. Yeah, let's leave it as a square root of 105. I mean, although you can square root 105 to get like 10.1, what value does that add? Right? I mean, it means you have to use a rounded value. So normally I would say if you can, just leave it as the square root number. There's no point in changing it. So let's say I ask you to write the 6 trigonometric ratios then. What is sine supposed to be equal to? It's supposed to be opposite over hypotenuse. What's the opposite? It's a good question. Since I have the theta listed right there, that's how you know. Does that make sense? Because it's a good point, right? You have to know opposite of what. So since the theta is right there, that's 105 over 11. What would cosine be? Adjacent over hypotenuse. Tan would be opposite over adjacent. No, that's not adjacent. That's hypotenuse. opposite over adjacent. Does that make sense? Okay, let's say I wanted to solve for theta. How do you get rid of this sign? Do you reciprocal sign or inverse sign? Good. So I want to make sure you guys know the difference then. If you're typing this in your calculator, you'd go second sign, so there's a -1, and then you'd type in root 105 over 11. I got 69 degrees basically. An error?
Yeah. Domain.
Oh, you gotta stop the square root sign. See the square root sign just keeps going there?
Oh.
You need to like 10 divided by 11.
Anybody else not get 68 degrees? Okay, now the point I want to make here is that if you want to solve for theta, this theta right here looks like it's 68.67 degrees. But did you have to use sine to solve for it? In theory, what you could do is you could second cosine, and you could have done cosine of 4 over 11. That should give you the exact same answer. Or what you could do is you could tan, nope, not tan, you'd have to inverse tan the root of 105. Make sure you stop that square root, like however your calculator does that, and divide by 4.
I keep getting the error.
But any of those three should give you the same answer.
Oh, I didn't put it back in.
Okay. Does that make sense? Okay. One more thought here. I actually did say the 6 trig ratios though. Yeah. So for the other 3, this is not hard work. I just want you guys to just know how these work, and mostly for next year. The opposite of sine is called a cosecant. All you do is you flip it upside down and make it 11 over 105. That's all. Or for cosine, cosine is known as a secant. You just flip it upside down and make it 11 over 4. Or for tan, you can call it a cotan, and it would be 4 over root 105. Here's the thing again, though. Why would you ever use these 3? Do you have a button in your calculator that allows you to do a cosecant, a secant, or a cotan? No. So if you had to, you would just flip this upside down and just use tan instead. So this is the extent of what I need you to know how to do. If you guys can handle that, that's it for the cosecant, cotan stuff. Okay? Okay. You know that example I just showed you there where there was an 11 and a 4 right there? We can actually place that on a grid. Remember how that other side was the root of 105? If we placed it on a grid, this point right here can actually be written as a coordinate point. This is back to that battleship concept that I kind of introduced earlier. What would the coordinates of this point be for x and y? Yeah, root 105 is your x value, because that's how far it was along the x-axis. And 4 is on the y-axis. What this is going to lead to is a bunch of new types of questions where I'm going to give you like a coordinate point, almost as like it's on a map, and we can use it to calculate angles. Okay. Do you guys know what sonar is? Like sonar, you might see like a picture of this in like a movie where you've got like the circles like this, and there's that little arm that like goes around in a circle and goes bloop, bloop, and like it. You know what I'm talking about, girl?
Yeah.
I'm not just making fun of myself here. Where like all of a sudden you'll be able to like figure out that there's like ships here and here and here. When I think of sonar, I think of like I don't know, like Soviet Cold War movies, Hunt for Red October kind of thing, where you're trying to figure out where these boats are. And what you could almost do is plot this boat and say this boat is at 6-9, and this boat right here is at 3-2. You guys know what I'm talking about like this at all? And what you could do then is you could make some triangles and figure out an angle between you and all of these other boats that are around you in 360 degrees. That's what I want to kind of show you guys how to do next. So, If we plot a triangle then on a grid like this, a couple of just little notation differences. We call it standard position, and we don't use A, B, and C anymore. All I do is I give you an ordered pair. All I will literally do is tell you this point right here as x, y. And what ends up happening is this side right here then is x. This side right here is y. And rather than calling this a hypotenuse, we actually use the letter r. Anybody have any idea why we use the letter r instead? Not ratio. It's close though. It goes in a circle.
Radius.
It's a radius. Yeah. If you kind of get my sonar example from the last question, you guys kind of see how it's going around in circles? It's almost like it's a radius to a circle is what this hypotenuse becomes. So all we do is we just change the letters around, x, y, and r instead. So it actually means that you might see stuff where rather than sine being opposite in hypotenuse, it's actually y and r. Rather than being adjacent in hypotenuse, it's x and r, and opposite and adjacent are y and x. That's all. Okay, let's try an example where we actually get to do something here. So here's a typical question I'll ask you. Plot the point 3, 6 on a grid. Where would 3, 6 go? That means go over 3, go up 6. I see how that would be 3, 6. Let's make a triangle out of it. We call it a standard position triangle. So we always draw that triangle back to the origin. In my mind, I like to think of the origin as like your position on the sonar. And, I don't know, the Russian-Soviet boat is over here at 3, 6. You can then draw like a triangle out of it, where this side is 3 and that side 6.
How would you know which line to draw, like that one?
We always draw down to the x-axis. That's the standard convention. Because you're kind of meaning you could draw a triangle like this. Yeah. Standard convention, we just defined it always as draw down to the x-axis. Good question. In terms of the things I've asked you to do here, then, it says plot the point P on a coordinate grid. There, I've plotted point P on the coordinate grid. What's the hypotenuse going to be? How can I find that?
3 squared plus 6 squared.
Yeah, whatever 3 squared plus 6 squared is. 3 squared plus 6 squared. That's 36. That's 64. It's 100.
3 squared plus 36? What?
Oh, 3 squared is not 36. 6 squared is not. Holy smokes, let's try that again. 3 squared is 9. 6 squared is 36. Add them together, it's root 45. Is that right?
Yeah.
Okay. I'm glad you guys are paying attention because apparently I screwed that up royally. Whoops. Right, if I were to ask you then how far it is from the origin to point P, the answer would be root 45. Or if you like my Russian-Soviet sub analogy, how far is it from you to the sub itself? 45, root 45, whatever units it is, I guess, meters, knots, miles, I don't know. Does that make sense? Then I'm going to ask you to find me the exact values of the primary trig ratios. So the primary trig ratios are sine, cosine, and tan. What is sine equivalent to? Okay, but we're changing that. It's now x. No, it's now y over radius. So what's your y value? And your radius or hypotenuse is root 45. That's all. Cosine is normally adjacent over hypotenuse, but your adjacent is really an x value. That's 3. And your hypotenuse is now that root 45, that radius. And tan is opposite over adjacent. Or for us, it's y over x. Does that make sense?
And those are the primary ones. If you ask for all 6, then you have to give the.
And that's actually what the next part here is. For the reciprocal ones, this is not hard. You just flip them upside down. So cosecant just means you do root 45. Oh my goodness, Chris.
Savannah Ryan, can you please come to the office? Savannah, please come to the office.
Root 45 over 6. Cosine goes with secant. That's root 45 over 3. And tan goes with cotan. That's 3 over 6. I once heard a story about a teacher who had a student who couldn't stop hiccuping. They went up to him and said, "I'll give you $20 right now if you hiccup right this instant." And the kid couldn't hiccup anymore. I don't have $20. I know. Okay, these three right here, these reciprocal ones, honestly, they have no use. Again, the only reason I want to show you this is just so that I have a little bit of a head start next year. That's all. They have no purpose, though. I cannot find one. These three right here are useful, though. Okay, because we can use any one of these three things here to find the angle, which is part D. Find the angle of theta, which is this little angle sitting right in there. So how do I go about finding that? Well, you do the inverse sine of 6 over root 45. There, my angle is apparently 63 degrees. Can you check your work? Let's try the next one. Inverse cosine 3 over root 45. Hey, it's the same thing. Maybe I'm not convinced yet. By the way, do you have to do all three of these? No, just do one, obviously, right? Second, tan inverse 6 over 3. Whatever, you guys get the point. Does that make sense? You guys able to follow that? Yeah. Okay, let's try another one here, because I want to finish before the end of the day. Can I skip ahead and do this one here that is 3, -8? Can we go to that one? Okay, your Russian Soviet sub-concept here. This is you right in the middle. Where is -3, -8? Yeah, way back here. Sneaking up behind you. They're approaching you on your rear flank. I also think of Top Gun when I think of this. Where you've got like the dog fighters or something like that, and all of a sudden now he's actually behind you, and now you've got a evasive maneuver because he's not in the front. Okay, when it comes to drawing this triangle, again, always draw the triangle to the x-axis, so it's going to look something like this. That's a -3, that's a -8. First thing we need to do is we need to find the hypotenuse. Okay, now when you take -3 and you square it, you still get a positive number, right? You still get 9. And when you take -8 and you square it, you get 64. Hopefully I'm not sucking at math right now. You should get root 73. Does that make sense? Just leave it as root 73. I mean, you can round it and call it, I don't know, 8.2 or whatever it's going to be. Just leave it as root 73. What are the trig ratios then? Okay, this is kind of tedious. Opposite? Okay, good question. Opposite of what? Where is my angle? You guys remember? There's an angle here, here, and here. Which one is the one that we consider to be the reference angle? It's this one right here. This is the angle that's called a reference angle. If I wasn't clear on showing you guys that earlier. We want to find this little angle right here. So compared to that, what's opposite? -8, and it'll be over root 73. While I'm at it, I'm just going to do the other ones here. Cosecant just means take root 73 and divide by -8. That's all. Okay, compared to the little angle in black I drew, and what's the adjacent then? -3. The hypotenuse, root 73. Cosine works in tandem with secant, so you just need to flip the fraction upside down. Last one's tan. Tan is your opposite over your adjacent. Why didn't I write the negatives? Good. Everybody hear that? I didn't write the negatives because you have -8 and -3, and 2 negatives will cancel. That makes sense. So, cotan then is just flipping that 3/8. Okay, here's where I need a little more context though. We're now going to solve for theta. If I were to inverse sine -8 over root 73, this is what I get. Let me know if you get something different. You guys able to get -69.4439? Okay. The explanation for why this is negative is probably best left till next year. Like I was saying with you guys earlier, I'm with Forster. I really hate that we do a little bit every year, but it's probably not worth confusing you by going on into the explanation for why it's negative. But the long story short is your calculator is going to give you an answer. It's not the answer we're looking for. Okay. -69 degrees. Can we just ignore the negative and just pretend it's 69 degrees? That 69 degrees is this little angle right here. The problem is, though, that's not theta. Because theta is all the way around the circle. So what we've just calculated now is that my reference angle is 69 degrees. But the actual angle that I'm looking for is 69 plus 180. Which is 249. That's actually the angle all the way around the circle behind you. One of the problems with trigonometry is that your calculator is going to calculate an answer for you, and we then have to use it, interpret it, how to figure out where it fits on our circle. Does that make sense at all? Let me try it again with cosine. If I inverse cosine, -3 divided by root 73. Oh, I didn't inverse cosine. Inverse cosine, -3 divided by root 73. I got 110.55. Anybody else get that when they solve that? Okay, again, this causes a huge problem because 110.55 is clearly not this angle right here, because that can't be 110. And it's also not the answer all the way around to here. I don't want to know where the 110.55 fits. Yeah. This right here is 110.55. Again, I can explain the why about this more later if you like, but what I need for you guys to be able to do right now is just kind of look at the answer it gives you and figure out reasonably where is that angle showing up. And the only place that 110 degrees could be is probably this little bit right here. Why don't I just call it 111? If 111 is this right here, how far is it the rest of the way around the circle? Well, what's a circle supposed to equal? So if you take 360 and you peel off 111, you get that 249, which is what I think we just calculated the other example with. Does that make sense? One more time here. The other possibility is I could try to inverse tan 8/3. If I inverse tan 8/3, my calculator is going to say 69.44. Again, is the angle all the way around to here going to be 69.44? No, so we got to use kind of our common sense and figure out, okay, well, where does that 69.44 really truly fit? And again, it's probably that inside angle right here. So if that inside angle is 69.44, if I add it to 180, then the entire angle is, again, the 249 degrees. Does that make sense? When it comes to trig, you have to be smarter than your calculator. Your calculator is going to give you an answer, but it might not give you the angle you thought you were looking for. We are always going to be looking for the angle all the way around to here. But your calculator might actually give you this angle instead, Or it might give you this angle instead, or it might even give you that number as a negative number. And you just need to use your interpretation skills and figure out what the angle is to the quadrant we're looking for. Any questions? Okay, one last example, then we'll call it a day. I'm going to skip the one involving cosecant. We'll just do this one here. There should therefore be two angles that allow cosine of theta to be negative root 3 over 2. Does negative root 3 over 2 ring any bells? If I were to plot a triangle, hopefully you guys remember this triangle by now. There's root 3, there's, yeah, that's not right. Ugh, that took away a lot of it. There's root 3, there's 1, there's 2. This is 60 degrees, that's 30 degrees. Which angle does theta have to be if cosine is root 3 over 2? 60? If it was 60, then it would be opposite and hypotenuse. Well, that's sine. So it's actually the 30, because the 30 gives you the root 3 and the 2. That makes sense? Here's the thing, though. If I were to take my calculator and try to type in the cosine of 30, it is not a negative number. How do I make it negative? $30 degrees is right here. Well, I could put that 30 degrees in a different quadrant. For example, if I labeled this thing in this quadrant right here, this would be a 1, that would be a root 3, and that would be a 2 right here. I still have an adjacent and a hypotenuse right here that are root 3 and root 2, but are either of them negative? I have to put the triangle in a different location. Sometimes I just need to show you how to do this. What if I put the triangle right here? I put it in this quadrant right here. If I took that exact same triangle and I slid it around in a circle, could you see how I could have like a 1 right here, a 2 right here, and a root 3 right here, and I'd still have 30 degrees right there? I'm kind of like flipping it around a little bit. But now there's one big difference. This 1 right here is going down. I would call it negative 1. This root 3 right here is actually going in the backwards direction, so I need to call it negative root 3. Now if I look for the cosine of this, what is cosine equivalent to? Adjacent over hypotenuse. Do you see how now I've made the adjacent negative? But it's because I took the triangle and I threw it in different quadrants instead. And so now I have adjacent over hypotenuse, negative root 3 over 2. But the angle is not 30. What's the actual angle all the way around the circle? 210 is right. Because the actual angle is all the way around here to 180 plus 30 more. So the true angle is actually 210 degrees. Try it.
Please excuse the interruption.
Cosine 210.
Here's a couple of announcements. Just a reminder
See how I get that
that
same
we
number?
are collecting money for
And now it's
adopted
negative.
families. Collection jars will be brought around tomorrow
There's
with
one more
class
location this could fit,
competitions.
by the
So
way.
make sure you bring some money tomorrow. London
What other
Davis,
quadrant could I put this in to make it negative?
please come to the office. Here's the gym schedule for tonight.
Right here.
B girls, 3:30 in the
Let's say
gym.
put a triangle in that
A
quadrant. I'll
girls,
just
5
redraw it here.
o'clock Granum. B boys, 5 p.m.
Could I make
Walk
this be
gym,
negative root 3?
And A boys,
This
6:30
2 and this 1. It's not negative 1 now, it's going up in the positive direction. But you see how I can plot a triangle in this quadrant here too? And it still has 30 degrees. I've like rotated the triangle and flipped it back around up into this quadrant here. See how the adjacent is still negative and the hypotenuse is still positive? But the opposite, I don't even care about opposite because it's about cosine. In theory, I should be able to find this angle as well. What would this angle be all the way around here then? 150, yeah. These are the two angles that should work, 210 and 150. Watch this, this is my last step here then. If I take the cosine of 210, it's the exact same as the cosine of 150, which is the exact same as the square root of 3 as a negative divided by 2. All three mean the same thing. Yeah. The long and short of what I want to show you is the idea that we can work with angles, but in different quadrants. The only twist is you get negative numbers because you're either going backwards or like down. You're going like negative by going in the other quadrants here. That's all. Okay, thanks for bearing with that. I got one more lesson, and then I'm gonna give you guys some work time finally. Sorry.